One open method in determining the root of a function is Newton Raphson. This is the most efficient solution by far. Learn more about it here in Numerical Solutions to C Problems. Saying that it is classified as an open method, Newton Raphson only needs a single point to start with. With a given function, say that the initial value has been identified, with x distance of x naught and y distance of f of x naught. Newton Raphson uses the tangent line to get close to the real root. The slope of the tangent line derives the function for the method. Slope is rise over run, which is then taken from the illustration as f of x naught all over x naught minus x1. Slope is also taken as the differential of the function, written as f prime of x. And when cross-multiplied, x naught less x1 then is equal to f of x naught upon f prime of x naught. Since we are looking for x1, transpose terms to have x1 is equal to x naught less the function of x naught upon f prime of x naught. So in a nutshell, the procedure of Newton Raphson is through differentiation. The problem to illustrate the method is f of x as 5x cubed minus twice of x squared less 4. Take the root of this function nearest the origin, and the preferred roots are positive. The accuracy required is with 4 decimal zeros, and the initial values should be whole numbers. First is to determine the initial values through assumptions. Looking for the root nearest the origin, we can start with 0. So the function turns into 5 times 0 cubed minus twice of 0 squared less 4, giving negative 4. With x of 1, the function becomes 5 times 1 cubed minus 2 times 1 squared minus 4. This gives negative 1. Then, with x of 2, the function turns into 5 of 2 cubed minus twice of 2 squared minus 4, giving positive 28. With a sign jump, we can deduce that the root we are looking for is within x of 1 to 2. With Newton Raphson, one can either use the upper limit or the lower limit. But to cut the process even shorter, we can start by taking the midpoint of the initial values. So x naught is half of 1 and 2, which is 1.5. If we take the f of 1.5, we get 5 times 1.5 cubed minus 2 times 1.5 squared minus 4, which makes 8.375. Placing everything in a table is a better option for the iteration. But first, we need to identify the function for f prime. If we differentiate the function, the first term is the derivative of 5x cubed, which is 15x squared, and negative 2x squared is differentiated as negative 4x. The derivative of a constant is 0. We can now fill the table, where the first x is 1.5, and the computed f of x earlier is 8.375. Next is to look for f prime of 1.5. That is 15 of 1.5 squared minus 4 of 1.5, which gives 27.75. Now we completed the first iteration. We continue to the next x, which is computed from the Newton Raphson function, which gives 1.5 minus 8.375 over 27.75, giving 1.198198. Solve for f of x, which then becomes 1.729778. Then f prime is solved as 15 times 1.198198 squared minus 4 times 1.198198, which is 16.74239. The third iteration starts with taking the succeeding value of x from the Newton Raphson function, where it comes out to be 1.094881. Complete the rest of the iteration by taking f of 1.094881, which turns out as 0.164993. Then also plug in the same x value into the f prime function, which becomes 15 of 1.094881 squared less 4 of 1.094881, simplified as 13.60194. Do the same process for the fourth iteration, as we are near the accuracy required. x4 then comes from 1.094881 less 0.164993 over 13.60194 to make 1.082751. Place this x value into f of x to have 0.002115. Then f of prime is computed with the same 1.082751, which gives 13.25424. Reaching two decimal zeros, we might have the answer with this iteration. So let's start with x5 by taking 1.082751 less 0.002115 over 13.25424, giving 1.082591. This is the value to be plugged into the f of x function, giving 0.000006, and also into the f prime of x function, which also results to 13.24969. Notice that f of x already surpassed the required accuracy of 4 decimal zeros, so the root is 1.082591. But let's try to converge the iterations too. By plugging the values from the fifth iteration, x6 turns out as 1.082591 minus 0.000006 over 13.24969, giving the same value as 1.082591. Take note that the one we subtracted is almost zero, which doesn't affect the first term anymore, thus giving the same value. F of x is then the same as the previous, and of course, f prime of x will also yield the same value. So indeed, the root for the function is 1.082591, with as short as just 5 iterations. The method of Newton Raphson is truly an efficient root finding approach.